Let's see. Let's see if it's live on Twitch. Okay, and let's see YouTube now. Okay, it's live on YouTube as well. Nice. Okay. Yesterday, when we left off, we added a billboard to the game. Not to the game, to the render. And now we'll be adding multiple different lights. Yeah, let's get into it today. Hopefully, we can also do the specular lighting today. Let's see how it goes.
Point lights. So I won't actually be covering any new Vulkan technique, but this will act as a good review of some of the stuff we've done so far and how we can add on to the existing engine. With the single point light we currently have, we are doing two things. We pass the point light information within the global UBO to the simple render system. We use this light information to calculate the illumination for each model object. And to render the point light, we also rely on the information within the global UBO to determine the billboard object's position and color. In the case of multiple point lights, things will change only slightly. The global UBO struct will now contain an array of nested point light structures. The simple render system will still use the light information from the global UBO to calculate the illumination for each model information within the global UBO to
Calculating lighting for each model, render the point light.
determine the billboard object's position and color. In the case of multiple point lights, things will change only slightly. The global UBO struct will now contain an array of nested point light structures. The simple render system will still use the light information from the global UBO to calculate the illumination for each model object, but now we'll need to loop through each light in the array, accumulating the total light intensity. In the case of actually rendering the point lights, there are a variety of ways we could do this. We could combine rendering every light into just a single draw call, with calculating the light's index within the point light shaders by using the vertex index. This is actually a really good solution, especially if rendering a high number of point lights, but not what we're going to do in this tutorial since I want to use push constants again. Instead, we'll just do one draw command per light, updating the push constant each time. Okay, so let's get to coding. Before we start updating the global UBO with an array of lights, we don't actually have any game object representation of our existing point light. We've just been using the values of what's in the UBO. If we're going to be working with multiple lights, it will be much easier if they have game object.
Let's say game object, HPPP. Some inputs. Inverse struct point light.
So to start, open the
Point light component.
transform component. I'm going to add a new component with struct point light component. A game object having this component will be how we signal that
Float light intensity. I don't think these will be needed, but let's leave it.
point light system. All
Pause 1.0
will called light intensity. For point light size and position, we will use the values from the transform component rather than creating duplicate fields. Then, on the game object, add a unique pointer with type point light component with a default value of null.
Okay, these aren't required.
We use a pointer here since we
We'll be adding it under transform component. Okay. STD unique pointer point light component point light equals
ability of having a null value. For example, the floor and base game objects aren't point lights, so they won't have this component set. Similarly, a point light object wouldn't have the model pointer set, which is how the simple render
optional pointer component.
not try rendering the point light. Following this, I'll declare a helper function called makePointLight, which can optionally take a light intensity, radius, and color values. This is just a convenience function to create a game object instance with a field set so that it is compatible with.
Yeah, we're doing this under create game object. Static only game object make point light float intensity equals 10.0 of comma float radius equals 0.1 f comma geoline vec3 color.
We could just create
So will be a white light.
empty game object as before and set each of these fields ourselves.
So
Whatever you want, a light intensity of 10 is probably actually a bit high. In the implementation file, copy and paste in the declaration. Don't forget to remove. In the implementation file, copy and paste in the declaration. Don't forget.
copy, go to the implementation file, the game object CPP. Paste. And let's copy this. Let's clean up all these folder files. I'll just close them. Yeah. Paste. All the game object.
The static keyword, as well as the default value.
Yeah.
Since default values cannot
All the game object.
present in both header and implementation.
Delete. Okay, function. All the game object.
Would expect. First, a point light size is only dictated by the radius value, which we'll store in the scale.x component.
All the game object. Game object. All the game object. Delete game object dot color, no, just transform dot scale dot x its radius.
Finally, create a pointer value for the point light component using the make unique function, and set the component's light intensity field to the provided intensity. So now we can objects.
Let's rename this to light game object 56. Light game object. Let's change it to light object.
Doing so, we are going to update the global UBO struct to support storing multiple point lights. In the first app implementation, I'm going to move the global UBO struct
First app CPP.
definition out of header. This way, if other files need
Control X and frame and forward. HPP.
to this definition, they will be able to get it. In my frame info header, I'll paste the definition in, and above it declare a new struct called point light. Well, first,
First define max lights.
lights constant of size 10. For each object in the scene, we need to iterate through each point light and accumulate the light's effects on the model. More point lights in the scene means more computation.
I really need max lights.
Performance.
I guess to like limit it, but wonder how bad it gets if you don't do it. Struct point light. Not a component, it's an actual object. Like for position, color intensity, radius.
A conservative limit of 10 for now. Of course, there are techniques to optimize to allow for a virtually unlimited number of lights, but that's well beyond the scope of this basic implementation. So in the point light struct, we just define a position and color. I'm making both vectors just to keep memory. Move the last two fields, replacing them with an array of point lights.
Can we delete this? There we go.
Lights. Finally, add a num lights field, which keeps
Global UVO, ejection matrix, UV matrix, ambient light color, light position, light color. This gets removed. Point light, lights max.
since not every scene will have exactly 10 point lights. Okay, let's move on to the point light system.
And num lights. Yeah.
First off, in the header, add a new void function called update. This function will be used to update the point lights array in the UB.
Void update. Then info. Info.
With the current values of any point light game objects in the scene. Then, by the top of the values of
And it has a global UV.
in the scene. Then, file just within the namespace.
Template. I can minimize these. No.
I'll create a point light push constant struct. At the beginning of the
So point light push constants. No.
mentioned that there were a couple methods we could use to render point lights, each with
Position, empty brackets, and color. Empty brackets again.
lights by index
Float radius.
the global UBO information, which has the advantage of only requiring a single draw call. However, by using push constants, it's easier to add extra information per light. The shader code will be simpler, but we require a draw call per light.
Control C.
And update the push constant range size to our
Size of this.
so we also need to update the push constant range count to 1.
1. Then ampersand paste. Push constant range.
Push constant range variable. Now it's time to implement the update function. The point light information will all be contained by the frame info game objects map, which needs to be copied over to the UBO point lights array. We'll use a similar pattern.
Okay, making the update function now. Update and global UBO.
Finds what game objects to render. We iterate through each key value pair of frame info.game object.
And light index equals 0 for auto Amazon KV. What is the syntax for this?
Get the game object reference using the kv.second field. We then need
KV frame info not game objects. Okay, but I was right about it needing the colon. Auto project KV second set explicit
which is easily accomplished by just checking if the
equal null pointer continue.
is null, in which case we can skip over this game object. So now that we know we are in fact working with a point light game object, it's time to copy it
Point light index dot position Austrial info. Translation color
We use the light index variable declared above the for loop to know which position of the point lights array to set, and we need to set both the position and color fields. since the translation component is only a vector.
Control C, Control V. Color.
Four. I have the W component set as 1, but this doesn't actually matter as this value will just be ignored. For the color field, the W component
Like 4. No visual light intensity.
lights light intensity. After copying to the UBO, we increment the light
Classic.
to the subsequent position in the array, and finally outside the for loop, we need to set the UBO num lights field. Whatever the final light
UBO num lights equal light and depth.
loop completes will be the number of lights within the scene. And that's it for the update function. But now we need to render multiple lights. This will be very close to how we currently render multiple game objects in the simple render system.
Control C, render the lights. So that part can be deleted.
Game object, skipping over any that does not meet the criteria for being a point light. This is of course kind of inefficient and something we'll address in a future tutorial. Next, we need to provide the point light push constant
Point light, push constants, push empty brackets, semicolon, push dot position, Control S.
within the for loop. Make a local push constant variable, setting the position, color, and radius fields. In the make point light function, we use the scale.x component to store our
GLM. Push dot color. Light radius. Point light dot radius.
here to extract the radius value.
Okay. Result of transform dot translation dot x.
Push constants function, we can pass this push data to the point lights pipeline. We have
Translation scale. And VK command push constants. Frame info command buffer pipeline layout.
the frame info's active command buffer. Next, we've got the pipeline layout. Remember that this is just the description of the set of resources
Let's put this into separate lines. VK shadow. Stage fragment flat, stage vortex web.
can be accessed by the pipeline. So in this case, when we created the pipeline layout above, we have both the push constant description and descriptor set layout description, which together are basically just telling the pipeline that it will have access to the point light push constant information and the global UBO information. The next field is the shader stage flag, saying make this push constant information available to both the vertex and fragment stages.
Let's move this up.
From our push constant struct, the size of the push constant struct, and finally the address of the push variable. The last thing to do is call the draw command for each point light object, so move that function call into the for loop from below. Okay, the point light system is complete. Now it's time to fix up our shaders. Since we've modified the global UBO
Let's go to the shadows.
We're going to need to update every shader file. Starting in the point light vertex shader, I'll declare
point light, vertex, point light flag. Let's just serve these up. Here's in the vertex and right above you. So point light, forward position, color radius. Okay.
position and color fields. Following that, add the point lights array with a size equal to whatever was the max size you declared in the frame info header. Vulkan has a concept known as specialization instance, which, as the name might imply,
Point light, max lights and no.
values into shader programs at the time of pipeline creation. So rather than hard coding this value of 10, we could instead pass it in as a specialization constant.
What else did you? Let's just leave it hard coded for now.
Point light struct definition into all 4 shader files. So we can replace the old UBO definition and now also have the point light struct being defined. Four shader files. So we can replace the old UBO definition and now also have the point light struct being defined.
Copy, Control C.
Okay, starting with the simple run.
I have to do it for all of them. Paste. Simple shadow, simple flag. I don't think. Okay, he's added it for these also. I was going to say, I don't think they need the point light thing here.
As is and requires no more changes. But the fragment shader now needs to loop over each light to accumulate the total diffuse light contribution. So we're going to first initialize the diffuse.
And simple shadow. Let's close out all these other ones. Okay, now we just have the shadows. Which one is it? Simple shadow what? But 3 direction to light. What? Okay, is in the fragment one. Oh, yeah. Like 3 diffuse light equals UVO dot ambient light color
Surface normal value.
into
The fragment surface normal
ambient intensity.
was the same for each point light. So I'm putting this here to avoid.
Tag like 3 surface normal normalize normal.
Recalculating the normal each time. Then we have a for loop that iterates from 0 to num lights. We can get the point light using I to index into the UBO point lights.
For I numlets plus point light
Then for each light, we need to calculate its diffuse light contribution to the total.
carry direction to light.
The direction to light calculation needs to be changed to use the index light position. The attenuation calculation can remain unchanged. And then
Right. Direction to light. Light position XYZ. Does not normalize though.
It needs to be changed to use light contribution. We can get the point light using I to index into the UBO point lights array. And for each light, we need to calculate its
Okay, let's remove this normalize.
to the total.
Delete.
To light calculation needs to be changed to use the index light position. The attenuation calculation can remain unchanged. And then to simplify the code a bit, I'll store the cosine of the angle of incidence into its own variable. So this is the same calculation as before, but we can
So attenuation float cause angle incidence. Cause yes. Control C. Yes. Yeah, I think we definitely need some plugin here just to like highlight things. Let's see, GLSL. Let's click install. GLSL support, apply. Scan update. And let's restart. Just back. At least this is getting recognized. Generation.
the computed normal above.
Okay, wait. Surface normal.
As its color times intensity times the attenuation.
Vec 3 intensity equals UO. Right.
Finally, we can add the intensity
Okay, light color XYZ into W into attenuation.
cosine of our angle to the total diffuse light value.
Uh-huh.
And that's it. This iterates over each active light, calculates its light contribution, and the
this all can be deleted. And let's hit save.
Or simply given by the total diffuse light times the fragment's color.
Look for diffuse light. Diffuse light into frag color and 1.
Now, navigate to the point light vertex shader. You should have already added the updated UBO and point light definitions, but
Point light vertex. Okay.
since yet. We can do this with
Yeah. Things are a bit better organized with the plugin added.
uniform, and then a type and variable name, which can be whatever you want. I typically just
Layout, push constant uniform push. And these are vec4. Position. Vec4. Color. Vec4. Radius. Should be float. Okay.
constant contains 3 fields, vec4, position, and color, followed by the float radius. We no longer require the light radius constant
Can delete that.
we provided on a per light basis. And all that's left to do is to update the position
Push. Position. Not
calculation.
XYZ.
UBO light position becomes push dot position, and the light radius constant becomes
Push dot radius.
next. Copy your push constant layout and paste the definition into the point light fragment.
Control C. Point light fragment. Paste. So
This is also a simple change. All we need to do is change the UBO dot light color to push dot color. Now you may think
push dot color.
and we almost are, but we haven't actually created any point light game objects yet. To keep things simple, let's first create just one. In the load
Save.
function of the app implementation,
First tab CPP.
objects make point light helper function. I'll set my light intensity to just 0.2.
Auto point light. An object. Yeah. This is symbol main. List initialization. Okay. Yeah.
Point light to the game objects map using in place. Getting
Let's save it. I just need to delete this. Make point light 0.2 f.
ID for the first
Then in place point light get ID, point light
argument,
move.
and std
Yeah.
move on the point light variable itself. So one thing to remember is that after you move the point light variable, it is no longer valid to access it again. One thing some programmers do is that whenever they plan to create a variable to then move it, is to limit its scope with a nested block. So this is something you may wish to do as well, but usually I don't bother.
Wait, what?
ID for the first argument, and std move on the point light variable itself. So one thing to remember is that after you move the point light variable, it is no longer valid to access it again. One thing some programmers do is that whenever they plan to create a variable to then move it, it is to limit its scope with a nested block. So this is something you may wish to do as well. But usually
Oh, interesting. So I can just do this. Move it up. Alt up. One shift. Interesting. I didn't know this was a thing. Let's see.
thing to do is to call the update function we added to the point light system. We'll do this in the update section of the application render loop.
Oh, let's see. Where is the update section? I'll just bring this to separate line so that it's more readable. Click into the run section, global UBO update. Yeah. Okay.
It obviously needs to be called
Point light system dot update framing for UBO.
we write to the UBO buffer. Now build and run your code in the section of the application render loop. Note that this function obviously needs to be called before we write to the UBO buffer. Now build and run your code and you should get a single point light object between the two phases, or wherever your origin is for your scene. Okay, but this tutorial is called multiple.
And let's test this out first. Make sure everything runs. Okay, shaders are compiling. Let's see how it turns out. Okay, the scripts are building. Okay, yes. Oh, is that going to crash? It looks like it. Let me rerun it. Okay, so okay. It is in the middle. The shading looks correct. This is the smooth waves. And this is the flat shaded waves. Not flat shaded, it's like a lower polish. Right. They both technically have the same form of shading. Is the light? Okay, it's a little above. Oh, it's setting it. Ah. Okay, that worked great. Let's save everything.
I provided a pastebin link of some rainbow light colors in the description below, which feel free to use those and paste them into the load game objects function. Then I'll create a point light game object.
Yeah, let's copy paste the paste one. Yeah. Control C. Yes. There we go. As yeah. For int equals 0. Less than light colors not count.
Object for each color in the light colors vector.
Dot size.
initial position for each light object, I'm going to create a rotate transformation. This will be a 4x4 matrix created using the GLM rotate.
And let's copy this and can delete this one. Say flat waves, flat with smooth is then floor and lefts. Yeah.
Function. The first argument is simply a 4x4 identity matrix, followed by I times 2 pi all over light colors.
And that game object pointlet, and we're making the pointlet. Okay. Now pointlet color equals light color R. Okay, they added a translation thing. And let's do auto rotate light. Chaitanya asked, can you explain what Vulkan is? So, are you familiar with what Unity or Unreal Engine or Godot is? They are basically software to make video games. And Vulkan is one of the softwares that is used to make that software. So it's a level below a game engine. It's used to make game engines. So if you've ever seen any game made with Unity or Unreal, then they likely have something like Vulkan as the foundation to create its software. It's significantly more complicated than just using a game engine, which is why they exist. But yeah, that's what Vulkan is roughly. Previously, there was a version called OpenGL, but that is now outdated. Yes, Vulkan is used to make game engines. So it is all the libraries and stuff that's used to make the game engine and handle all the rendering and things like that. It's also used for Blender, any 3D rendering. Can do 2D rendering also. That is that. Let me just finish this. GLM. Rotate. So once I finish this little bit of code, I'll be able to show you what can do. This is a much more basic version compared to a full game engine. But that's kind of the point of doing it this way. GLM 1.0. Let's make this explicit. Save. Equals GLM rotate. Set enter, save. Angle, and then this. Set save. 1.0, then GLM 2 pi. I'm just learning it to refresh my C++ skills, and I'm also in the game development scene, so it's always helpful to know what the foundational software does. So it's just like a thing to like learn extra skills. C++ I haven't used since like 12th grade, so that's also a nice refresher. And it's also a more advanced project. So you do end up like learning new ways of using C++ than what I learned back in school. Are you considering uh, learning Vulkan or anything else? C float divided by right color size. And this is minus 0.0, 0.0. And shall unrotate it, not for 1.0 to pi float, brackets and brackets. Yeah.
into equal-sized slices, and then rotates each point light incrementally farther around the circumference. This will have the effect of creating a ring of lights. The final argument is the axis of rotation, which will be the up vector, and for my engine, that is 0, -1, and 0. So I'm going to make the initial translation of the point light to be the rotation matrix times the position
Control X, Control V. And let's make those GLM Vec3 rotate light.
I was using for the point light in the previous tutorial. Now
doing -1, -1, 1. Yeah. But we haven't got it done. Yeah.
point lights with the center of the ring at 0, -1, 0. As the final addition for
Yeah, let's hit run and test it out. Okay. Let's see if it all builds. Let's go. Yeah. So Chaitanya, yeah, this is what the software looks like once you run it. Right now it's like a very, very basic word. Thanks for subscribing, Chaitanya. Want to share my side? I'm grade 12th at present. I'm going to pursue CSA, AML, attention span, and retention power. Those are two things I don't know how to help you with, particularly. I need understanding of physics and chemistry for entrance exams, but I'm good at maths and computer science. Yeah, for me, physics and chemistry wasn't my particular strong suit either. But like if you're going into like AI ML stuff, depending on the job, you might need physics or chemistry. So, for example, if you were getting into AlphaFold, you would have to know how chemistry and all works to some degree at least. And if you are doing like these AI models that are supposed to help create like 3D worlds or whatever, you're going to have to know how physics works as well. You know, there are a lot of complicated things. But like if you're in 12th grade and I'm assuming CBSE, you've already got through most of it. Like if you're going for tuitions and stuff, should be fun. Like how bad are your grades? Everything is running. The lighting's also looking good. Yeah, nice.
Actually, animate the
For attention span and retention power, I don't know if this is good advice, but when I was first starting to learn stuff, I was doing it during COVID. And for me, initially, I was like, let me just do 5 minutes of like something. My friend had recommended one website to just like learn some programming languages. So sololearn.com. This was the website I was using. There are various courses and things. Um, yeah, I was just doing like 5 minutes a day. Um, just like start small, like choose the smallest amount you can do. 35 out of 70 in both physics and chemistry. Of I don't know how the scoring is nowadays, but I assume it should be better. Are you like going for tuitions or like extra classes or anything? Because having a good teacher can make quite a big difference. Because for me in our school, the teachers in school wouldn't really teach that well. In order to make money, they would uh, not teach that well, but they would have tuitions, and over there they would teach better. So typically, if you go for tuition, they will teach you better. I'm not necessarily talking about 67 out of 70 in CS is very good. Uh, yeah, definitely like focus on CS, but uh, I think this is currently in C++. Using some the like Vulkan libraries and some other libraries, but yeah, this is basically C++. And this is just like a project that I'm just using to learn Vulkan. That's it. After this project, I'm planning to go back to focusing on some Unity projects, maybe. I'll have to see. I'll decide that once I'm done with this. I'll also have to see if I'll be busy in the coming weeks because over here it's going to be a busy season. So I might get some freelance work during that time. Um, During the busy season, you don't get a lot of free time. So I'll have to see what my plans are for the future. But yeah, this is C++. It's running.
light matrix and navigate over to the point light systems update function. This is
Oh, there's even more at the end of this.
a good place to update the point light game object's positions. First, we
Anyway, point light update, point light system, HTTP, CPP.
that will rotate each light proportional to the amount of time elapsed between frames. By using the frame
Uh, I was a computer science student, but now I'm working. Currently, I'm like in between jobs, so this is just another thing to like add to my resume as well. Currently, the job market here isn't particularly good for like normal game dev jobs. So I'm trying to expand into like more normal software engineering stuff. which is another reason for this project. So yeah, it will, if I'm currently I have like all of my projects are more developed towards game development. So having something like this might be more helpful for general software engineering roles. Oh yeah,
time variable.
right. As in the update function.
Then is a good place to update over actually animate the point lights as well. If we copy this,
Okay, let's copy this. Control C. Update.
and navigate over to the point light system's update function, this is
It's after continue. Yeah.
a place to update the point light game object's positions. First, we can create a rotate matrix that will rotate each light proportional to the amount of time elapsed between frames by using the
Alright, let's delete this. Of this up. Oh, it's above light index. Yeah. GLM angle is frame info frame type. Frame info dot frame type. What error am I getting to? Okay, it still requires us. There we go.
dot frame time variable. Then we simply need to update the game object's translation to equal the rotation matrix times the previous translation value.
Yeah, let's simplify this. Will it all fit here? Save and save. Save. Okay, it all fits in one line.
You should also try animating other properties of a point light, such as its intensity or color.
We'll update the position as well. And let's see. Paste. Object transform translation. Object. Kind of liked it when it was separate lines. Let's bring it back there. And we'll move into save. It's adjusted. Let's hit save. Yeah, this is not the same. No. Rotate layer GLM vec4 object transform translation 1.0f. Yeah.
It is probably a good idea to add in an assertion that the point light game objects in the scene haven't exceeded the limit specified by the max lights constant.
And let's see. Insert light max lights. And
Exceed this limit, you will at least receive an informative error message.
yeah. Point lights exceed max maximum specified. And let's save all this. We can remove this, I imagine. Right.
That the point light
Does it
UBS
delete it from the?
that will point to the point light system's update. The final addition for this tutorial, we can actually animate the point lights as well. If we copy this rotate light matrix and
Okay, we're just copying it. Let's see. Let it load. Okay, the lights are all animated. The lights are animated on the ground as well. Nice. Let's see if there are any issues with resizing. No, there are not. Okay. Nice.
Anyway, that's it for today. Thank you for watching and keep on coding. Cheers.
What's the time now? 4:51. Okay, I still have time for one more. Let's do the specular lighting. First, let's save all of this. 25 multiple lights. Commit and push. And all of it gets saved properly. Anything on the shelf. And delete it permanently. Nice. Specular lighting.
Hello, coders. So back in this previous video,
Let me update the titles. Multiple lights and specular lighting. Update. Let's see, as it gets updated on Twitch. Let's see on YouTube. Okay, it's updated here as well. Let's play a game of chess as a refresher. Let's change the UI for this. Presets, let's do nature, cosmos, ocean, metal, marble, gothic. Wood, green angle. This looks interesting. Let's do the wood one. So let's save. Let's play again. Bots. And let's play. Let's attack the queen. Attack it again. And miss out. Let's bring this here. Okay, make that very strong. If I bring my knight here, can attack this. Okay. I'll just make some protests, develop the pieces. Let's kick this knight out. Let's push this back. Capture. Probably should have captured with the pawn, but let's castle this way. All its pieces are over here. Let's bring this here. And this is a free piece. Is going to bring push this forward. Let's attack the queen. Oh, let's grab it. Yeah, we ended up equal in that exchange. Let's bring this here. Capture. Can do N% also. That just makes me move. Let's capture this way. So we'll attack this. We'll just grab it. In this piece, we can still double attack. Let's still give a check. Let's attack here. Let's see. Let's capture here. Watch this. I made a mistake. Oh, whatever. Let's attack both of them. Capture that one. Let's grab that. Let's attack this. Let's bring this. Let's grab this. Let's jump this forward. Protect. Let's go here. If I can win this rook, I can win. If he captures, I get another pawn. Okay, let's move everything off of the dark squares. Yeah. Let's see, let's attack this king. Uh, keep checking. Check. Hmm. Let's clean that up. So yeah, Mhm. Let's bring this here. Prevent any form of stalemate. Then anywhere. Nej. Yeah. Got it wrong a few times, but it's done. Now let's go back here.
I first showed the light transport equation and explained how we often rely on lighting models which only approximate the light transport equation, but are simpler graphics hardware. So far, we've covered the Limburger model, also known as diffuse shading. It makes the assumption that the surface reflects incoming light equally in all directions. This is a very basic model that works well for non-metallic matte surfaces. The Blin-Phong model builds upon the diffuse shading model by also supporting shiny materials. Shiny materials tend to reflect light more strongly in the direction opposite the angle of incidence. This is known as specular reflection. A mirror, for example, would be a perfect specular reflector, while smooth surfaces like metal and plastic are less perfect, but specular lighting still has a noticeable effect on their appearance. A reason for these differences are microfacets on the surface of the material. These microscopic bumps and grooves cause slight deflections in the reflected light rays. Smooth surfaces will reflect the light more ideally, with the reflected light being strongly concentrated around the theoretical ray of reflection. With rougher surfaces, the reflected light can be scattered in more possible directions, resulting in a less concentrated cone of reflection. The key difference between this and the Limburger model is now the position of the viewer actually matters. With the Limburger model, we assume light is scattered equally in all directions, meaning that regardless of the camera position, the point on
Okay, interesting. Never consider that your point of view will matter for the lighting.
the material will look the same. With the Blin-Phong model, the light intensity is greatest the closer the viewer is to the theoretical ray of reflection for each fragment. In many cases, none of the reflected light will reach the viewer. You should already have a natural intuition about this. It's the reason why when looking at a shiny material, the location of the highlight changes as you move around. There are a handful of models that try to approximate specular lighting, each with their own pros and cons. I'm not going to delve into too much detail as to their differences. For a detailed look, I'm not going
Form model, blend form model, Gaussian model.
to delve into too much detail as to their differences.
Sure.
For a detailed look, check out this resource here. A Gaussian model can more accurately approximate the microfacet distributions different materials may have. Both Phong and Blin-Phong models don't use a real statistical distribution and kind of just make things up. This means they violate things like conservation of energy. However, they require less
Not based on reality. Simple, more
computation
complicated.
and look good enough for our purposes currently. Also, we will implement physically based lighting for rendering materials more realistically in the future. So the Gaussian model just isn't necessary for us right now. So how exactly do these models work? Well, the main idea behind the Phong model is we calculate the dot product between the ray of reflection and the direction to the viewer. The dot product is a nice function for this because it is a measure of the angle between two vectors when normalized. The dot product result varies from 0 when perpendicular to 1 when parallel. Negative values will be ignored. Next, we take this result and raise it to some power. The parameter here affects the sharpness of the highlight. For example, a brushed metallic material may use a value of 32, while a smooth metallic material would have a much higher value of like 512. These values are somewhat arbitrary since they don't correspond to any physically based model. So our inputs to the power function will always be between 0 and 1, meaning that the output range will be between 0 and 1 as well. A higher exponent more quickly crushes lower values to 0, resulting in a smaller region where the specular component is bright, hence the sharper highlight. As the final step, we combine the diffuse and specular components together to determine the final color for each fragment. The Phong model has some limitations. Most notably is that the angle between the direction to the viewer and ray of reflection must be less than 90 degrees for the specular component to be non-zero. For smooth materials with a sharp highlight and a high exponent, this isn't much of an issue, since the specular light should be very concentrated. However, for rougher materials, it should be possible that a non-insignificant amount of specular light is being reflected to the viewer at an angle surpassing 90 degrees, which the Phong model
So much of this is just
doesn't really account for.
explanation.
The Blin-Phong model, on the other hand, overcomes this limitation by first calculating the vector directly between the direction to the light source and the direction to the viewer. This is known as the half-angle vector, which can then be compared with the surface normal to determine the specular intensity. When the direction to the viewer is perfectly aligned with the ray of reflection, the half angle will be perfectly aligned with the surface normal, which is the same behavior as the Phong model. But the angle between the half angle and the normal will always be less than 90 degrees, which avoids the main limitation of the Phong model, where it can't account for angles larger than 90 degrees. One last addition that is common
again. My whole computer
commonly made is to add a
screen has crashed. Good thing I saved everything. Let me. Okay. Let me just make sure the rest of the streams are working. Okay, let's see Twitch and YouTube. It's still loading. Yeah, seems like it.
equation, and explain how we often rely on lighting models which only approximate the light transport all directions. This is a very basic.
Yeah, we will. Let's read the comments of the previous one. We're also like 6 minutes into this. Let's go through the comments. That's always a fun part. He's back. Managed to create a Lorentz attractor visualization. What is this? Switch. What is this? This is some weird form of graph. You'll have to say something about mesh shaders in the series. Want to implement dynamic number lights. Just what I'm saying is
Hello, coders. In today's
comments of
degrees. One last addition that is commonly made is to add a control term to configure the strength and color of the highlight based on the material. This is an RGB term that is multiplied by the light color and specular light intensity prior to combining with the diffuse component. Most often it is useful to make this a neutral value less than 1. However, for some materials such as gold and other metals, this term can be set to the material color because highlights on metal can take on the surface color.
color, diffuse lighting, color, or specular lighting.
Can be set to the material color because highlights on metal can take on the surface color. Anyway, let's get to coding. The first thing we're going to do is update the global UBO struct within the frame info header, as now we will need to access the camera's position. Rather than directly
Yeah. Let's close this. Now, okay, global UBO. And for HTTP.
the camera's position, I'm actually going to provide the inverse view matrix. Using the inverse view matrix, the camera's position can easily be extracted from the last column.
GLM mat for inverse view matrix.
If ever in the future we need to transform a value from camera to world space, we will have that functionality ready to go. Next, we need to add the inverse view matrix calculation to the camera class. In the camera header, I'll declare and initialize a 4x4 inverse view matrix field.
Camera HVPP GLM inverse view matrix.
Then, in the camera's implementation, we currently have two functions which update the view matrix, with the idea being that whenever the view matrix is updated, the inverse view matrix should be updated as well. And because their construction is so similar, no extra calculation
CPP
to be done. I've provided a paste bin link in the description below. The only
view matrix, inverse view matrix. What are the changes?
differences are the upper 3x3 position is transposed. In the
Okay, interesting. Let's still copy it to make sure everything is typed correctly. Control C. Paste. And this is transposed. And this is no longer dot product.
the final column is now simply just the position. This should make sense since another way to think about the inverse view matrix is as the equivalent to the model matrix for the viewer game object. Really,
Camera size tools, please.
we could have just used that instead. Next, in the set view yxz function, we should also paste in the code to set the inverse view matrix. And if you've added any of your own custom functions to set the camera matrix, make sure
Set view XYZ here.
update the inverse view matrix.
So add a 0.
Before moving on, we need to go back to the camera header as I forgot to create a getter function for the inverse view matrix. This will be just like the other getter functions, returning a const reference to the camera inverse.
Camera HVPP. Const get matrix and get view. Const GLM. Not forget inverse.
Okay, now in the first app implementation, all there's to do is to set the UBO's inverse view field to the camera.
First app implementation. Inverse matrix camera.get inverse.
And just like last week, since we updated the global UBO definition, we're going to need to update all the shader definitions as well. So open
All the shaders have to be updated.
your shader files at the map.
Control C. Paste. 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 Save.
Field in the same position as the definition in the frame info header, and then copy the global UBO uniform to your remaining 3 shaders. Now, as a quick sanity check, if you build and run, everything should still be working as before. Okay, now we can actually get on to implementing the spec.
Okay, let's build this and check. Yeah, it's running correctly. And it crashed. Yeah. It's running.
Lighting model. Head to the simple fragment shader, and by the top of the main function, I'm declaring
Simple fragment shader.
type vec3 called Specular Light. This will
Vec3 specular. Yep.
each point light specular contribution. Following that, we will extract the camera's position in world space from the inverse view matrix by indexing into the last column and then selecting the first three components with .xy.
Vec3 camera position world. Uploads UVO dot and inverse view matrix.
We normalize the camera's position minus the fragment's position
Your direction normalized
to
camera
get the surface vector
position.
pointing to the viewer. This will be used when calculating
Fragment.
the half angle vector. And that's all the pre-calculation shared by each light. Now per light object, first I'm going to normalize the direction to light vector within the for loop. Make sure to do this after setting the attenuation, otherwise the distance calculation will be incorrect.
Direction to light. Pose. Normalize. Direction to light. This is equal. And we just normalize, and now we need that version for the attenuation.
Normalizing the view direction is no longer necessary in the angle of incidence calculation. So I'm doing repeat the normalization function. I believe normalization is a pretty optimized function on modern hardware, but still it's best not to recalculate unnecessarily. Okay, now let's compute the specular component for the light. The half
Specular lighting. Vec3
is equal to the sum of the direction to light
shift of 6.
and we will
Normalize direction to light plus view
normalize all of that as well.
direction.
The blend term can then be calculated using the dot product of the surface normal and the half angle.
Okay, shift 6. Blend on.
Clamp this value to the 0 to 1 range.
A dot
This
surface
is when the viewer and light are on opposite
and half angle.
sides of the surface. And then we raise the
Blend down upwards. Clamp. Blend on 0 to 1.
some power. A higher exponent will be a sharper highlight, and in the future we can pass this
32.0.
into the shader so that it can differ between all. Next, we can calculate the specular contribution as the light color times attenuation times the blend term.
Specular light color. light color, note XYZ, note attenuation into linter.
Final step is to add the total specular light to the output color. I haven't included the control
Plus specular light
at this point yet since we're not passing it in. So for now,
into specular.
at least I'll also just multiply by the fragment color, which, as I mentioned before, is what you would set the control term to in the case of some metallic materials. Now, if you build and run, everything should look much shinier. Also, to check that things are working correctly, is that as you move the camera, the specular light should also move. This is easier to notice when using a sharper highlight. Now, before you go, I just noticed a small mistake. I forgot to multiply by the light's intensity when calculating the specular value. This here should use just the intensity value we calculated above. If I rebuild, the specular reflections are still noticeable, just much dimmer now.
Okay, this was supposed to be intensity.
Anyway, that's enough for today. Thanks for watching and keep on coding. Cheers.
And let's pull this. It looks much shinier. Let's do the previous version just to see. And now it's like purely metallic looking. And it crashed. Yes. Let's build again. Oh, nice. Let's go through the comments. Working classic series tutorial around an object-oriented architecture of my own. And I wanted to extend this first version by integrating wireframe or PBR shading. Keeping updated work in engine tutorial with full-time Java is hard. And months ago. I recommend you do lighting calculation in view space, camera relative world. Otherwise, the lighting math will break down when camera scene is too far away from the origin due to the way floating point precision works. Also, one question, because I couldn't find. Is there a way to make the window draw during resize? It's a bit trickier than you might expect unless there's a better way I'm not aware of. Blocks events while resizing is occurring. and I'll see you to global. I'll go.
Hey everyone. So far, up until now,
Yeah, this is the last one. Chronos put this on the main learning page. Alpha. Best tutorial series. Did Journal C++ engine and OpenGL tutorials. It's 5:30. Let me continue this tomorrow. Okay. So let me save all this. 26. Specular later. Not in push. Yeah. Should have finished pushing. They're all nice. Yeah. I'll end stream here for today.